Have you ever thought about a world where antibiotics become ineffective? A world where modern medicine as we know it is outran by evolving bacteria? So have we.
Welcome to our exploration of the future of medicine, Next-Generation Antibacterial Drugs, or NGADs.
My name is Morgan, and this is Vish, and we're here to answer all of your questions on the next generation of antibacterial drugs. In this video, we will discuss 5 primary topics. First, traditional antibiotics and antimicrobial resistance, or AMR. Second, NGAD's role in combating AMR. Third, an explanation of NGAD's mechanisms. Fourth, recent innovations in NGAD collaboration. And finally, ongoing industry challenges.
Traditional antibiotics, like penicillin, cephalosporins, and tetracyclines, have revolutionized modern medicine. This technology has monumentally reduced mortality rates from bacterial infections since its discovery in 1928. Modern medicine has relied on traditional antibiotics for years, causing strains of bacteria to evolve and develop immunity against common types of antibiotic technology. According to the World Health Organization, the misuse and overuse of antimicrobials in humans, animals, and even plants is the main driver in the evolution of AMR.
According to the World Health Organization, there are nearly 5 million global deaths per year associated with AMR. However, public health isn't the only facet of society that is affected by AMR. The World Bank estimates that AMR and its impact on modern medicine could result in $1 trillion in additional healthcare costs by 2050, and anywhere from $1 trillion to $3.4 trillion GDP losses per year by 2030. Another marker shows the significance of AMR is that while the number of deaths per 100,000 people decreased by more than a factor of 20 from 1900 to 1980, it doubled from 1980 to 2000, partially due to the increase in AMR bacteria.
So, AMR clearly demands innovation. The next generation of antibacterial drugs use approaches that have evolved from traditional antibiotics, but employ nanotechnology instead to kill bacteria. More specifically, NGADs employ intrinsically antibacterial inorganic nanoparticle metal materials, which can cause the physical rupture of the cell membrane of bacteria without using antibiotics.
The key difference between these traditional antibiotics and NGADs is that traditional antibiotics cause chemical damage to the membrane of the bacteria, whereas NGADs cause physical damage to bacteria.
NGADs will not only be able to treat infectious AMR diseases, but they will also attack key facets of the infection to make it susceptible to traditional antibiotics moving forward. The goal of this evolution of antibiotic drug is to treat all the diseases that traditional antibiotics can, and potentially more, without being affected by or increasing AMR.
And while NGADs offer the benefits that we have described, there are several challenges that the industry must still first overcome. While there are many actors and stakeholders involved in NGAD research and development, there's still a high demand for this technology to address AMR bacteria. This outlines a key problem with NGAD technology. R&D is plateauing.
Non-traditional approaches to combating bacteria require deep innovation, and per the WHO, that level of innovation, i.e. nanotechnology, has not yet been introduced to clinical trials. This plateau is occurring for 2 primary reasons. First, while there is an increasingly high demand for a technology that addresses AMR, there is a lack of funding in the field. This is in part due to many pharmaceutical companies pulling out of investing in antimicrobial drugs because of their high capital costs, long research timelines, and low return on investments. Antibiotic drugs treat acute illnesses instead of chronic illnesses.
Second, some of the technologies which would make NGADs more effective or more potent, like nanotechnology and CRISPR, are not fully yet understood or developed themselves. Therefore, like many technologies, NGADs are somewhat dependent on the innovation or co-innovation of other technologies. The intended outcome of NGAD technology is to permanently remove the risk of bacteria becoming resistant to antibiotic drugs.
So, to overcome these challenges, there are many actors from the private, academic, nonprofit, and governmental sectors that are dedicating time and resources to designing effective and affordable NGADs.
Corporations such as the Mayo Clinic and multinational drug companies like Pfizer, Johnson & Johnson, GlaxoSmithKline, the AMR Industry Alliance, and GARD-P have started to influence the research, development, and potential deployment of next-generation antimicrobial drugs so that they can be equally or more effective than the previous generation of antibacterial drugs. Companies like GARD-P have supported the AMR Action Fund with a mission to address the lack of efficacy in modern healthcare due to AMR investing in companies engaging in R&D to combat AMR.
In the world of academia, universities such as Arizona State, Oxford, Manchester, and Duke are all huge R&D centers for NGAD. In doing basic scientific research, these institutions have been able to secure funding that serves as grassroots resources for NGAD research and development, which has changed the approaches of all other sectors as well.
Speaking of funding, nonprofit organizations such as the International Center for AMR Solutions, the Bill and Melinda Gates Foundation, and the Wellcome Trust have all made efforts to fund NGAD R&D.
As the AMR crisis has grown, federal government organizations like USAID, the CDC, NIH, the FDA, and the World Bank have started to influence the research and development and deployment of NGADs and have even passed laws such as the GAINS Act and the 21st Century Cures Act. The World Health Organization, for example, through its Global Action Plan on Antimicrobial Resistance, is focused on creating antibacterial drugs with no AMR side effects.
Additionally, existing international and governmental organizations are making efforts to foster relationships between industry actors, governments, and NGOs to further both R&D and advocacy in the AMR field. All of these actors are essential in the work of next-generation antibacterial drugs. Without them, we would be facing an ever-increasing threat of antimicrobial resistance. So thanks to the scientists, politicians, and both private and public sector leaders, we will be able to see a world in the future where antibiotic efficacy is increased.
So, there you have it. While antimicrobial resistance has become a global health crisis, the world's brightest minds are paving the way for the next generation.
And while NGADs is an important innovation for the foreseeable future, they are by no means the final destination or iteration of this technology. So keep working, keep studying, and keep researching.